Hi there, welcome to this video. We are going to talk about finding volume through integration of area using cross sections of a solid. Previously, we've looked at finding the area between two curves, and we will eventually find volume by generating a given region around an axis. But today, we're going to look at what is known as cross sections. Now, very simply, a cross-section is just a slice of a solid. And imagine you're playing Fruit Ninja and you're slicing those fruit. What you kind of see when you make that slice is the cross section. So if I were to slice an orange or a soccer ball, you would see a circle. Well, that would be your cross section. Okay, and so we can accumulate these areas of these two-dimensional shapes in order to get a three-dimensional shape, which will give us total volume. Okay, so in these examples, the bounded region is what is going to be our base of a solid. It's going to be our base, and the cross sections will point up out of the base. And here's a couple of examples to go ahead and illustrate. You can see the region is y equals x squared and the x-axis, and you have these two-dimensional shapes kind of sticking out, right? So this distance, top minus bottom, is just a square, and then you can see, as you get, your base gets bigger, it comes out bigger, and you get all of these squares. So I could get the volume of this shape by accumulating these integrals. Here you can see some triangles. Here you can see these look like rectangles. So where the height, what's coming out, is a certain multiplier of the base. And here we have some semicircles, okay? So, and also too, to give you a dimensional, on my website here, I have an example where I have this region, and we have some squares. So you can see I have this distance here between my blue function and my red function, and these are squares that we're looking at, okay? And if I go ahead, I can increase the number of squares, and you can see how it becomes a solid object, okay? But this is what we're going to do. We're going to calculate the area of these objects and then accumulate them all together. While visualizing these shapes may be tough at first, the actual calculus is straightforward and logical. Remember that calculus requires us to create one small piece of what we want to know, and then the definite integral accumulates all of those tiny pieces in order to find the volume. So some important notes about volume by cross-section. The problem will state to find the volume using a definite integral. And our representative rectangle will act as the base of whatever shape we're using. Our rectangle will always be perpendicular to an axis, either to the x-axis or to the y-axis. If it's perpendicular to the x-axis, we're integrating with respect to x. If it's perpendicular to the y-axis, we're integrating with respect to y. We simply need to find the area Gosh, it's not letting me write. Oh my gosh. Let me try zooming out. Of the given cross-section using our representative rectangle. Some problems simply give the area, and these are like the easy ones. They give you the area without giving a shape. Don't overcomplicate this. It's very important to remember here that volume is equal to the integral of area. Okay? So, with that as a foundation, let's go ahead and look at kind of some of the steps. So, step number one, you want to go ahead and you want to draw the representative rectangle perpendicular to the x-axis. So draw the representative rectangle perpendicular to the given axis. 2, set up the integral as follows. The integral from a to b of the area of the cross-section shape. If you're integrating with respect to y, make sure your bounds are also in values of y. And then number 3, find the formula for the area of the given cross-sectional shape based upon our representative rectangle. Remember, height/length of a rectangle is always the base of the shape, okay? The limits of integration are the same as before. Just make sure that you use x or y depending upon what you're integrating with respect to. And answer the question that is asked. Does it want you to just set it up? These are the best because we just have to set it up. Or does it want you to answer? So let's go ahead and look at an example here. Here is example number 1, and they say, let R be the shaded region in the first quadrant enclosed by the graphs of y equals e to the power of negative x squared, y equals 1 minus cosine of x, and the y-axis is shown in the figure. Now notice they give us the two curves and they tell us which curve is nice. That's nice. And then they say the region R is the base of the solid. For this solid, each cross-section perpendicular to the x-axis is a square. Find the volume of this solid. So here's kind of your clue. They say find the volume, and they say for this solid, each cross-section to the x-axis is a square. So if I want volume is going to be equal to the integral of the area. And so what I have to go ahead and do is I need to find my area. Now the area is a square, and so if it's perpendicular to the x-axis, this right here tells us that it is dx, and our height is going to be our rectangle, representative rectangle is going to be this region right here. So I'm taking this slice, and this is the base of a square, and what comes out is going to be the same distance. It's going to be the same distance. So I have a whole bunch of squares that are going to be popping out of this region. If I can draw. Okay, and so just imagine a whole bunch of those. So what is the formula for a square? Well, it's s squared. It's s squared. And this is going to be our side. So what is this distance? Well, it's this top function, whatever it is, okay, minus whatever this height of this bottom function is. Okay, so always top minus bottom will give us this distance, right? Top minus bottom, that's how you find distance. So I have e to the power of negative x squared minus this bottom function, which is 1 minus cosine of x, okay? And make sure you notice how I put parentheses because I'm subtracting that bottom function. There's two terms, so put parentheses to when you subtract that whole region, okay? And I want this to be squared. I want this to be squared, okay? There you go. Now, something that I don't have is my bounds. Now, do notice I do have 0, so I know that my lower bound is 0, but what I need to do is I need to figure out where is e to the power of negative x squared equal to 1 minus cosine of x. And so this is AB1. This is going to be a calculator active question. So I'm going to go ahead and identify what this bound is. Okay, so using my graphing technology, I went ahead and I graphed both functions here, and we can see the intersection is this location here, 0.94, x equals 0.94194, and I'm going to use all of those bounds, or all of those digits, and I'm going to call it A in my problem here. And I do this because once I identify a certain value as a variable, I can call it A up here. And on the TI Inspire, you can store this value. You can click on that value and you can store it. Again, here I guess you could copy it if you wanted to take those values. But that is my value of A. Okay, and so I have to go ahead now and I have to calculate these values. So again, since this is calculator active, we can go ahead and set up this integral. So we have the integral from 0 to that value, which was 0.94194. And then our integrand was e to the power of negative x squared minus, in parentheses, 1 minus cosine of x, okay, dx. And there is our value, which is 0.591. All right, and there you got it. That's how we find volume. You integrate area, and our area formula, or our area shape, is square for this example. Let's go ahead and look at example number 2. In example number 2, this is also a calculator active question. They say let R be the region in the first quadrant bounded by the x-axis of the graphs of y equals ln of x and y equals 5 minus x as shown in the figure below. So here they don't tell us which one is which, but I think it's fairly easy to go ahead and see that your natural log function is right here. Here's our natural log function. And here is our negative linear function. Okay. So they say here, right? The region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. So again, this is a square, right? But do not evaluate an expression involving one or more integrals that gives the volume of the solid. So since this is relative to the x-axis, again, I'm going to go ahead and I'm going to find the volume by integrating the area with respect to x. And so this is s squared. S squared, that's our formula. And so what I'm doing again is I need to go ahead and calculate this area. What I'm going to do is I'm going to split this into two integrals because this function's on top for here, so I can measure this distance here, right? So this will be the integral from 1 to wherever this intersection is, and again I'll call this A here. I'll call this A. And so this distance is going to be our blue function, which is the natural log of x dx, plus now I have the integral from A up until this value here, which I believe is 5, right? 1, 2, 3, 4, 5 of 5 minus x dx, okay? And so what I have to do is I have to go ahead and say, hey, where is the natural log of x equal to 5 minus x? And again, this is a calculator active question, so we can find this. So natural log of x, 5 minus x, and it looks like they intersect here at 3.6, so x equals 3.69344. And I'll call this A, and there we go. Oh, these need to be squares though. This is just that distance. So what I have to do is I have to square this. Square, square, and now we have it. Okay, so there you go. Integrate area, which is a square, so s squared, that distance squared. All right, example 3. Example 3 is going to be different because, again, here they give us a function f, and they say R is the region in the first quadrant bounded by the graph of y equals f of x and the vertical line x equals 1, as shown in the figure below. Region R forms the base of a solid whose cross-sections are perpendicular to the y-axis, which are squares. Again, they say write, but do not evaluate an expression involving one or more integrals that gives the volume of the solid. Okay, since they say perpendicular to the y-axis, it's very important for your representative rectangle that we are drawing our representative rectangle this direction. And so you can kind of see that this rectangle here, if I'm going to integrate area with respect to y, that this is going to be this value, which is 1 minus this function right here, which is f. So f right here, that is e to the power of 2x. So 1 minus e to the power of 2x, that would be this distance right here, okay? And so I'm going to go ahead and put this squared. But what's very important to note is that my function kind of gets cut off here. They only want quadrant 1. So, you know, this really is only good for this region up from 1 up until this value up here, which is e squared, So what I'm going to have to go ahead and do as well is I'm going to have to add in another integral, right? And this is dy, another integral of this area right here. So again, right minus left, this is just 1 minus 0 dy, and our bounds here are going to be y equals 0 to y equals 1. So 0 to 1 dy. And I guess you could put a power of 2 on that if it's a square. I don't think it's going to matter much because 1 squared is 1. So anyway, there is your volume to find this region. Again, it's perpendicular to the y-axis, so we have dy. My bounds are in terms of y, from y equals 1 to y equals e squared. And my, this is, again, since it's a square, the side, this distance is going to be my right function, which is just 1, minus my left function, which is e to the power 2x. Okay, last example I have for you here, but this one is going to go ahead and kind of outline the variation. Everything really has been squares so far, so we'll generalize it with the square to make you feel comfortable, and then we'll change the shapes, okay? So again, here's a region R, base of a solid. For this solid, the cross-section perpendicular to the x-axis is defined as the shapes below. Write, but do not evaluate an integral expression that gives volumes for each solid, okay? So very, very important here. What I'm going to do is I'm going to write a general expression. The volume is going to be equal to the integral of the area, again, and our bounds are 0 to 1 dx, right? So 0 to 1 are the bounds, and we can see that here and here, and it's with respect to x. Okay, so how can I evaluate this distance? Well, this distance is f of x minus g of x. F minus g. So how does this adapt based upon the shape? Squares. Okay, so this is going to be the integral. This is going to be the integral from 0 to 1. My pen is not wanting to work. Okay, I think I got it to work, hopefully. Integral from 0 to 1, and that distance again is going to be f of x top minus bottom, and it's squared dx, okay? So that's a square. What if it was a quarter of a circle? A quarter of a circle. Ooh, this is kind of where it gets fun. Because if this is, oh my gosh, here we go. Okay, if this is a quarter of a circle, I kind of have this distance sticking out, and then you can kind of see this right here. So here's a quarter of a circle. Well, that distance is just going to be the radius. So now f of x minus g of x is equal to a radius. So your radius is equal to f of x minus g of x. And so this integral is going to be from 0 to 1. Well, the area for a circle is pi r squared. And if I want a quarter, them to be quarters, well, I'm going to divide by 4. Okay, so something you can do here is you can pull that pi fourths out front, and then it makes it much easier. And again, here on the inside we have our f of x minus g of x. So f of x minus g of x dx. Okay, now this changes. What if it's a semicircle? Now, let me go ahead and edit this up here. So that was a quarter circle. What if it's a semicircle, half of a circle? Ooh. So now what you're looking at is diameter. F of x minus g of x, that distance is diameter. So how do I find radius? Well, I have to take half of that. Okay, so again, I'm going to go ahead and take the integral from 0 to 1. A semicircle formula is pi r squared, but a semicircle is divided by 2 dx. So this will be the integral from, I'll pull my pi half out front, 0 to 1, and then I have my radius squared. Now your radius is not f of x minus g of x. That is your diameter. So how do we find radius? Cut it in half. Okay, so watch out when you're using circles. Just make sure you know if you're using the radius, what your representative rectangle is, if it's a radius or if it's a diameter. Okay, number 4, rectangles with height 4. Rectangles with height 4. Again, I have an integral from 0 to 1. A rectangle is base times height. So my base is f of x minus g of x, f of x minus g of x, and my height is 4. So I guess I could put, maybe I'll do this, maybe it won't be so confusing. So there's my base, and my height is 4 dx. So there you go. That's it. Okay, what if the rectangles have a height that's twice the base? So now what I'm going to do is I'm going to change it. So 0 to 1, okay, the base is f of x minus g of x for a rectangle. But I need to go ahead and now multiply times the height that's twice the base. So the height is going to be 2 times f of x minus g of x. So there's base times height, and all of this is again with respect to dx. So you would probably see that written like this. The 2 times the integral from 0 to 1 of f of x minus g of x squared dx. Okay, last one, isosceles right triangle with one leg as the base, Okay, so an isosceles right triangle, just to familiarize you, right? So these legs are going to be equidistant, and then I have a right triangle, so then we have our hypotenuse here. Okay, so this is the base, and sticking out is going to be the base, okay? Or is going to be the base, but which is really the height. So again, I have the integral of 1/2 base times height. This is for a triangle, 0 to 1 dx, okay? So I do know that my base is f of x minus g of x, f of x minus g of x. And since the height is going to be the exact same, right, if it's sticking up out of it, it's going to be f of x minus g of x squared. Okay, and let me see if they have, they have equilateral triangles. So this is a little bit different here, but if they were isosceles right triangles, this distance coming up straight up out would be the same height. So that would be your height. Okay, all right. So hopefully that helps kind of show you, just how the different shapes look and how we calculate volume using cross sections. All right, that's going to do it for this lesson. I'll see you in the next one.